welcome back to another video. Today we'll actually be looking at physics 0625, the extended syllabus of course. And this first video in this first video I'll try to cover everything for general physics. Let's pray this video isn't like 3 hours long. I'll just try to speed run it. So this one, again, I'm following the syllabus order. So according to that, the first topic that we need to look at is physical quantities and measurement techniques under motion, forces, and energy. So you need to know how to use a ruler, which we all know, to find the length or volume of an object. Now, there's nothing really to talk about here. The only thing I'll mention are some of the errors that occur while using rulers. So number one, you need to avoid parallax errors. These are errors that occur when your eyes aren't really perpendicular to the measurement, so you end up getting false readings. So you just need to be mindful of that. And also zero errors, where, for example, you're trying to measure, let's say, a table. Okay, that doesn't really make sense. You're trying to measure the distance between these two lines. However, most rulers don't really start from zero. They usually have like buffer pieces on both ends. So if you were to just put it in between, your reading is going to be false because it fails to take into account this extra length that isn't accounted for the scale readings along the ruler. So you should also be mindful of that. Well, that's the easy stuff out of the way. Now we get to the not really hard stuff. This is also easy. There are two types of physical quantities. Physical quantities being those that can be measured, of course. You have scalar quantities, and then you have vector quantities. Now, scalar quantities only have a magnitude, whereas vector quantities have both a magnitude and a direction. So examples of scalar quantities that you must know are number one, distance, speed, time, mass, mass, and energy. These are the ones that you must, energy and temperature. Now these are the ones that you must know according to the syllabus. Let me add on a few more just for your knowledge. Work done is a scalar quantity. So yeah. And yeah, okay. These are scalar quantities. Again, all the quantities that I just listed have a magnitude, but they do not have a direction. Some students look at distance and think that it's a vector quantity, which is kind of fair. It is a fair assumption, but it's not. Distance is a scalar quantity, it does not have a direction. Vector quantities some of the vector quantities that you must know include force. So forces have direction. Another one that you need to know is weight, because the weight of an object is always downwards. Velocity. So velocity is very similar to speed. The best way I can describe it is that velocity is speed with a direction. Acceleration is a vector quantity. Acceleration. So acceleration isn't the same thing as speed or velocity. I think a lot of students confuse that, but we'll be looking at that later on in the chapter. Momentum is also a vector quantity because it deals with moving bodies. Electric field strength, I think that's obvious because of the directions, because electric field lines show the direction. Electric field strength. Yeah. Also gravitational field strength. Gravitational field strength, also known as acceleration of free fall. We'll be looking at that more in depth later on. Gravitational field strength. A few more that I would like to add are displacement. Displacement is a vector quantity. It's similar to distance, but it is not the same thing. I'll explain the difference between displacement and distance later on. Moment of a force. The moment of a force is also a vector quantity. Also, quick note, the moment of a force is not the same thing as momentum. You'll see why later on. Yeah, so these are the vector quantities that you must know. Again, these vector quantities have both a magnitude and a direction, whereas the scalar quantities only have a magnitude. Right. Now we come to, we talk about resultant vectors. So let's just, right. Now the next thing that you need to know based on the syllabus is how to determine the resultant of two vectors at right angles. And this can be done either via calculations or using a graphical method. So first off, let's define what a resultant vector is. Let me write it down so you know what I mean. Resultant vector. So a resultant vector is a vector quantity that has the same magnitude and direction as the combination of two or more vectors. So basically, it's the effect of combining two or more vectors. And at least in the scope of the IGCSE syllabus, you only need to consider resultant vectors when two forces or velocities meet at right angles. So let me just draw a quick example. If I have, let's say, a force in this direction, and I have a force in this direction with a right angle, when the forces meet, the resultant vector will be somewhere here, and it's the direction and magnitude is just the combined English. I'm joking. So the resultant vector or the resultant quantity has its magnitude and direction will be influenced by its successive or its predecessors, if that makes sense. So now we just need to, I guess, figure out how we can find the resultant vector. And as I mentioned before, that can be done based on a graphical method or by using a calculation. So you can use Pythagoras theorem. I think the second method is easier. We all know Pythagoras theorem. So the resultant vector is equals to x square plus square root of x square plus y square. So let's say this is 10 centimeters and this is 5 centimeters. You can just do square root of 10 square plus 5 square, whatever that gives you, and that would be the resultant vector. The graphical method involves you drawing this diagram in a graph book. So the diagram that I just drew would be in a graph book, and you would use a suitable scale to represent the vectors on the graph. So you could perhaps use 2 centimeters to represent 10 newtons or any other suitable scale. You would of course draw straight lines whose lengths represent the magnitudes of the vectors based on whatever scale you choose. You would then use the two lines to complete a rectangle. So what I mean is you would then, once you draw these two lines, you could use dotted lines to essentially create a rectangle or a square. And once you do this, you just measure the length from this corner to this corner and you have the resultant vector. But and that's not really a practical way of doing it, and it's easier to just use Pythagoras theorem. Now, one thing that I do want to mention before we continue with the syllabus, I'm not really going off syllabus, but this is going to help you with your paper 2s especially. You need to know about unit converting from one unit to another. This includes multiples and submultiples. So I'm just going to list some out for you. The multiples that you should know are, just a second, multiples. So you have mega, mega, which is a capital M. This is 10 to the power 6. You have kilos, so kilometers, kilograms, it's represented with a capital K. It's 10 to the power 3. Those are the ones that come up in questions the most. Submultiples, these are the smaller ones. Submultiples, the ones that you should know are micro. So this is the symbol for this is this, and it is 10 to the power minus 6. You have milli, which is a small m, and milli is 10 to the power minus 3. You have centi, which is a small c, and that's 10 to the power minus 2. And then you have, those are about it. These are the ones that come up the most. So you need to know how to convert from one unit to another, and I've just given you a quick summary of the standard values that you could use. Now we come to the second, topic in general physics, which is motion. Now, before we even begin with what's in the syllabus, I would like to explain the difference between distance, and displacement, because they are far from the same thing. So distance is just the space between 2 points, and is measured in meters, and it's a scalar quantity. Displacement is also the distance. Displacement is just distance in a specific direction. It's measured in meters as well, and it's a vector quantity. Now, the definitions alone won't help you understand the difference between the two, so it's best to use an example. If I have a moving body that's going 3 kilometers north, and then it goes, let's say, 4 kilometers south, east. The distance traveled by the moving body is 7 kilometers, 3 plus 4. However, the displacement of the moving body can be found using the Pythagoras theorem, which would be square root of 3 square plus 4 square. Once you plug that into your calculator, you get you would get 5 kilometers. So the displacement is 5 kilometers due northeast, because remember, displacement is a vector quantity. So that's the main difference between displacement and distance. Now, two things that you should note here. If a person were to walk in a circle, let's say person A, for whatever reason decided to walk in a circle, the distance that's traveled by person A is just the circumference of the circle, which is 2 pi r or pi d. However, the displacement is 0 because person A just ended up in the same place where they started. So that's another important thing that you should note down. Right, so now we can finally start treating what's in the syllabus. Now the first thing that we should do is, number 1, define speed. Speed is the distance traveled per unit time. It's a scalar quantity and is measured in meters per second. So speed, which is represented as v, is equals to distance represented with s over time. Speed equals distance over time. Velocity is speed in a specific direction. Practically speaking, you don't really need to worry about the difference. You just need to know that they have the same formula, they're measured in the same units. It's just that speed is a scalar quantity and velocity is a vector quantity. And from that you can derive that velocity is the speed in a given direction. Right. Now I want you to recall an equation from checkpoint, that being average speed. Average speed is the total distance that you travel, total distance over total time. Now you may be asking, why am I making this distinction? Well, in practicality, let's be honest, it's very unlikely that a human being walks at, let's say, a constant speed. Rather, their speed is going to vary across their journey. However, if, let's say, in a span of 60 minutes, I want to calculate your average speed in that 60 minutes as you were walking. The best course of action for me would be to just take the total distance that you travel in the 60 minutes and divide it by the 60 minutes, which is the total time, to find the average speed, rather than maybe doing something else, because your speed was varying. So that's really the only thing that I can do. And okay, now we get to some confusing parts. You need to know how to sketch, plot, and interpret distance time and speed time graphs. Now this is very important, so pay close attention. Right, before we go to the graphs, I made a mistake. I should explain what acceleration is, so that I can draw the distance time graph and the speed time graph at the same time. So acceleration, as I mentioned, is not the same thing as velocity or speed. Acceleration, just a second, acceleration is the change in velocity per unit time. I should write this down because it's an important definition. It's the change in velocity per unit time. So you can acceleration is the change in velocity per unit time, or you can simply say that it's the rate of change in velocity. I think the easiest way to understand what acceleration is through its formula. So acceleration, which is a, is equals to change in v. This triangle symbol is called delta. It's a Greek symbol, and it just means change. So change in velocity over time. And you can write change in velocity as v minus u, where v, okay, that's a little confusing, v minus u. I hope that's easy to read. So v is the final velocity and u is the initial velocity. So v minus u over t. Basically, acceleration, when we say that an object is accelerating, we say that as time goes along, its speed is increasing. Whereas if I were to say that the speed of a body is increasing, I'm saying that it's traveling a larger distance per unit time. Those are not the same things. It will be even easier to understand once we start drawing the graphs. But before we do that, speed and velocity are measured in meters per second. I think we all knew that. Over here, acceleration is measured in meters per second squared, which is not the same thing. Meters per second squared. Right. Now let's get to the graphs. Right. So this is a distance time graph, and it shows distance along the y-axis and time against the x-axis. You'll notice that I drew a few different colored lines. That's to make it clear and to denote a few things for you guys. So a straight line across in a distance time graph denotes constant speed. So that's for straight lines, constant speed. The green line, which is kind of a line that curves like this, shows decreasing speed. Decreasing speed. The red line, which is a horizontal flat line, shows that the body is stationary or it's at rest, which means that it isn't moving, stationary. And finally, this blue line, which is a curve like this, shows increasing speed. Speed. Right. Now there are a few things that you need to note here. By calculating the gradient of a curve for a distance time graph, you can find the speed, because if you know from your checkpoint knowledge, a gradient would be something along the lines of, let's say, S2 minus S1 over T2 minus T1. Let me just show those points here. T2 would be here, this would be T1, let's say, right? And here we would have S2, S1. So from this you can deduce that when you calculate the gradient of a curve in a distance time graph, you're basically just doing distance over speed, which is speed, and thus the distance over time, which is just the speed or velocity. So the gradient in a distance time graph is the speed or velocity. Now if there's constant speed, you can simply choose any point. Let me use purple. You can simply choose any point if it's constant speed, and then just calculate the gradient like this. But for increasing or decreasing speed, you're given a point, and you need to use a ruler to draw a tangent. It's hard to draw on the tablet, but you would usually draw a tangent like this, and you would use the tangent to calculate the gradient for this specific point. And the same thing would be done for increasing speed, where you would be given, let's say, this point. You would draw a tangent like this. That's not really right. Maybe something like, you need to try and get the angles equal. And a tangent, of course, is a line that only touches a circle at a particular point, and you can calculate the gradient like this, basically. So that's a speed time graph. Gradient shows speed. If you want to, so that's more or less it for a distance time graph. Let's go and look at the speed time graph. Right. So this is a speed time graph where speed is on the y-axis, and a speed time graph where speed is on the y-axis and time is on the x-axis. An upward facing slope or an upward going slope denotes acceleration. A straight horizontal line in a speed time graph will basically denotes constant speed. If you recall back to the distance time graph, you'll remember that over there a straight line would show that the object is at rest, but over here it denotes constant speed. Basically, you can see that if I were to draw a dotted line, let's say this is S1. So between this, let's say between A and B, the speed of the moving body is s1, which is a constant speed. Hence we say that the straight line shows constant speed in a speed time graph, and a downward facing slope like this shows deceleration. Now, there are two things that I didn't draw here. Number one, let's use a different color. If I have something like this on a speed time graph, that's decreasing acceleration, and it's kind of similar to the decreasing speed curve in the speed distance time graph. And if I have something like this, that's increasing acceleration, which again is similar to the increasing speed curve in the distance time graph. Now there are four things that you need to know. If you were to calculate a gradient and your gradient was positive, that means that's acceleration. If you were to calculate the gradient and you got a negative value, that's deceleration. The area under the curve, so if I were, you can see this is a trapezium. So if I were to calculate the area under this curve, I would get the total distance that has been traveled by the body. Whereas before, if I wanted to check the distance in this distance time graph, I can just look at the x-axis. Another thing I want to mention, constant speed is the same as 0 meters per second square. So constant speed is zero acceleration, if that makes sense. Because if you calculate the gradient here, if you were to calculate the gradient along this area, you would just get 0. So constant speed is 0 meters per second square. And also, this is a fifth thing that I want to add. Deceleration is not the same as decreasing acceleration. What do I mean? Decreasing acceleration, which was a curve similar to this. When we say that a body is experiencing decreasing acceleration, the speed of the body is still increasing per unit time. It's just that the rate at which the speed is decreasing, the rate at which the speed is increasing reduces. So let's say before, every second a moving body got faster by 5 meters per second. But for whatever reason, suddenly, it only started getting faster by 2 meters per second every second. So it's still getting faster, it's just getting faster at a lower rate, which is why we call it decreasing acceleration. Deceleration is straight up just a decrease in speed per unit time. So speed just starts decreasing as time goes on, and which is why decreasing acceleration and deceleration are not the same thing. And that's, well, so we're done with defining acceleration. We've looked at constant acceleration and changing acceleration. We know how to calculate acceleration from the gradient of a speed time graph. We know that deceleration is negative acceleration, right? Which if you recall, I mentioned the negative gradient thing. We know that we know how to describe the motion. Right. So after this, I'll be talking about free fall and terminal velocity. Just a second. Right. So the only thing left for us in motion is free fall and terminal velocity. So let's start with that. Okay. So let's tackle what free fall is. Free fall, or G. Acceleration of free fall, or G. Okay, there's a lot of like theory in this, so I'll try to draw a diagram to make it easier to understand, but you need to try and follow along with what I'm saying. So usually an object is said to be falling freely if it falls under the influence of gravitational force alone without any resistive forces acting on it. So if I have object A, for example, and it's falling, And this downward force is, of course, gravitational force. Usually, there's air resistance acting on the ball. But if we say that air resistance is insignificant, which, take note, in a lot of paper 2 questions, if an MCQ question mentions that air resistance is insignificant or opposing forces are insignificant, then they're trying to make a reference to free fall. So you should use whatever knowledge you have about free fall to answer that question. So when an object falls under the influence of gravitational force alone or without any resistive forces, it falls freely. Now what does this mean? It means that there are no external forces on the ball aside from gravitational force, and as it falls freely, the rate of acceleration is constant, which means that it falls at a constant speed. The rate of acceleration is constant, which means that on a speed time graph, the acceleration is denoted with the straight upward facing slope. And on Earth, the acceleration of free fall, which is this small g, it's also called gravitational field strength, but this acceleration of free fall has a value of about 9.81 meters per second square, and we can usually round that to about 10 meters per second square. That's the acceleration of free fall. Right. So now we look at terminal velocity, which is quite different. Okay, before I mention terminal velocity, I'll say force is equals to mass times acceleration of free fall. So let's say an object is 5 kilograms. Let's say an object of 5 kilograms is moving. You can calculate the force using this formula, where A is the acceleration of free fall. And the reason that weight is a force is because basically you have mg, mass times gravitational field strength. Mass is a constant in both, and g and a both represent acceleration. So if these two are the same, that means these two are also the same. Hence, weight is a force. And that's all you need to know about free fall. Now we can go to terminal velocity. Now, as I mentioned before, free fall doesn't involve any external forces, which is not really practical. In real life, when an object falls, say if I have object A falling, and this downward force again is the gravitational force. As it falls, it's going to experience air resistance, which I mentioned before. And this, as it falls and the velocity of object A increases, the air resistance also increases, right? And at a certain point, what's going to happen is that the resistance or the air resistance is going to equal the weight of the object. So you would have a situation like this. The air resistance, which is a force, will equal the weight of the object. And at this point, there's no resultant force acting on the ball, causing the ball to fall at a constant velocity. So graphically, you could represent this on a speed time graph. A speed time graph. Speed time graph. And before, if it was accelerating, it now undergoes decreasing acceleration and then constant speed. And this constant speed is the maximum velocity with which the object will fall until it stops falling. And this constant speed velocity is the terminal velocity. This right here. I don't have space, but this is the terminal velocity. So terminal velocity succeeds decreasing acceleration of a falling body in real life. That was a mouthful. I think now finally I can say that we know how to describe the motion of objects falling in a uniform gravitational field and with and without air resistance. So yeah, that's acceleration of free fall and terminal velocity, and we are officially done with motion. Now we'll be looking at 1.3, which is mass and weight. Mass, weight, and also density. It includes density, mass, weight, and density, right? So, mass is a measure of the quantity of matter in an object at rest that's relative to the observer. Basically, it's the amount of matter in an object. That's it. It's a scalar quantity, and which means it has no direction, and you would usually measure it using a digital balance or even a beam balance. Weight, on the other hand, is the force, or it's the gravitational force on an object that has mass. So if you have mass, by proxy, you're going to have weight. And in that sense, you can say that weight is dependent on mass. We call quantities like this derived quantities. Weight is a derived quantity. You don't need to know that because it's not part of the IGCSE syllabus. What you do need to know is that weight is a vector quantity, which I mentioned way back. Right, I forgot to mention, mass is measured in kilograms, weight is measured in newtons. That's newtons, as in Isaac Newton. Newtons, the symbol is a capital N. So weight is measured in newtons. And I already mentioned the formula, but weight is equals to the mass times gravitational acceleration of free fall, or the gravitational field strength. Right. And you can obviously rearrange this formula as G equals W over M. I think that's self-explanatory. You should also know that weight and masses may be compared using a balance. That's also self-explanatory. And I think we all know how to describe and use the concept of weight as the effect of a gravitational field on a mass. Yeah, I kind of explained that before. So now we move on to density. Density is just the mass per unit volume. Let me write that down. Density, which has the symbol rho, it's a Greek symbol, it looks like a P, it's called rho, is the mass per unit volume, is the mass per unit volume per unit volume, and we can say that rho is equals to mass over volume. Again, we've all learned this in checkpoint. The SI unit for density would be kilograms per meter cube, and you can the most lengthy thing that you need to know with regards to density is like the procedures that are needed to measure the density of certain objects and solids. So let me just do a bit of drawing real quick. Right. So if I have a regular solid, such as, let's say, a perfect cube, such as this one, it's very easy to measure the density. First, I would take a digital beam balance and use that to measure the mass of object A. I could then, because it's a regular cube, I could simply use a ruler to measure the dimensions, and I could then, by proxy, calculate the volume, and then I just do mass over volume to calculate the density. It gets tricky when you start talking about irregular objects. So an irregular object would be something like a stone. Let's say, like this, a stone. How do you measure the volume of the density of this? So number one, you measure the mass again using a beam balance. That's easy. You can measure the volume via displacement of water. That involves having two measuring cylinders, right? Okay, that's too big. It involves having two measuring cylinders, two identical measuring cylinders per se, and they have the same volume of water in both of you have the same volume of water in both of them. Well, okay, just a second. Right, sorry, my bad. You don't need two measuring cylinders. You only need one. But I still had to draw two. Let's say this is the before and this is the after. Right. So let's say this is 500 centimeter cubes of water. I can attach this stone to a small string and lower it into the solid. I can lower it into the liquid. And because the pebble itself occupies space, I'll see the water get displaced. And right, I'll see it get displaced. And so I can thus calculate the volume of the stone by taking this value. Let's say this is 520 centimeter cubes. I can just do 520 minus 500, which is 20 cm cube. So I can find out, I was able to find out that the stone is 20 cm cube. And then I just do mass over volume to find the density. The next thing you need to know is how floating works. Basically, an object will float in a liquid if its density is lower than the liquid's, and two liquids will not mix if their densities are different. For example, oil and water. I think, yes, oil is less dense than water, which is why it floats and sits on top of water. And with that, we are done with density. Now we move on to forces. And now we start forces. Now, a force is the rate of change of momentum, or it's the change in momentum per unit time. And from this, you can determine that a force is basically equals to change in momentum. So that's change in mv over per unit time. So over time. And you can, by proxy, say that this is mv minus mu. Final momentum minus initial momentum over time. And if you were to factorize the mass out, you would have F is equals to mass times V minus U over T. And if you remember, V minus U over T is acceleration, which is how we can find out that F is equals to ma for ma. And the main thing I want to say here is that this equation is usually more important than this one, even though this one is more common, and that's because it's derived from this one. Or rather, I should say, yeah. So this longer equation at the top is the predecessor to this one over here. And you'll see more questions that use this one, so that's definitely something you need to keep in mind. Now, if a force is applied to a body, it can cause changes in shape and size. And these changes and the degree of the change in the shape or size can often depend on the elasticity, which I'll discuss in a bit. Right, and by in a bit I mean right now. So elasticity is the ability of a material to regain its shape and size after deformation by a force. So something like a rubber ball, if hit by a force, will become like compressed or squashed, and it will start occupying maybe less space, but it then regains its shape, assuming you don't hit it too hard, which is kind of the concept of Hooke's law, which falls under elasticity. Hooke's law. Now, Hooke's law states that the extension of an elastic material is directly proportional to the applied force, provided its proportionality limit is not exceeded. Now, what this means is that the force applied on my rubber duck or rubber ball, for instance, let's say that's F, is directly proportional to the extension. So the greater the the harder I hit my rubber duck, as in the more force I apply on it, the greater the degree of deformation. And once it does get deformed, it will regain its shape. However, everything has a limit, right? So my rubber duck, for instance, it has something called a proportionality limit, where if I apply too much of a force, it becomes permanently deformed. And you can actually represent that graphically. Before I do that, F is directly proportional to X, where F is force, X is extension. You can actually get an equation from this where F is equals Kx. K is a constant. It's called the spring constant. You can also call it the stiffness. And I'll explain what that is in a second. But obviously you can rearrange the formula to get K equals F over X. And based on this, let's draw a load force diagram, a load extension diagram, sorry. Right, so this is a load extension diagram where the load or the force is on the y-axis. Of course, it's measured in newtons, and the extension x is on the x-axis. X and x. The SI unit would be meters, but practically speaking, you would use centimeters, which is fine as long as your units are correct. You'll notice that between A and B, between points A and points B should be here, sorry. Between points A and points B, you have a straight line, which shows that between points A and B, you have a straight line, which shows us that as the force is increasing, the extension is also increasing at a proportional rate. However, after point B, you reach the proportionality limit, where no matter how much force you apply, the body becomes permanently deformed, which means that it's likely to extend less, and at this point Hooke's law is no longer obeyed. And now we come on to the calculations that I mentioned. Because this is a straight line, you don't need to bother with the tangent stuff. And if you were to calculate the gradient, you would get the spring constant, which is K, or the stiffness, which is K. The SI unit for K is Newton per meters, which is this. But again, in most graphs, practically speaking, you would use centimeters. So you can still say Newton per centimeters. You just need to be mindful of your units. And that's a load extension graph. Let's just look at the syllabus real quick. You need to know how to sketch, plot, and interpret load extension graphs for an elastic solid and describe the associated experimental procedures. Right. I'm going to get to the experimental procedures after this, but you also need to know how to define spring constant. Right, so spring constant is a force per unit extension. It's derived from the formula, because K is equals F over X, right? K is equals F over X, so which is force over extension, force per unit extension. That's the definition of the stiffness or spring constant. I mentioned the proportionality limit or the limit of proportionality. I showed you how to identify it on the graph. Now there's also something called elasticity limit. Technically speaking, proportionality limit is the point where Hooke's law is no longer obeyed. And elasticity limit is the point where at the proportionality limit, there's still a deformation and the object will still likely regain its shape. However, the force and the extension aren't directly related, which is why you see like the curved bit over here. However, the elasticity limit is when there's permanent deformation and it doesn't regain its shape any further. But you don't, according to the syllabus, you don't need to know that. We'll be looking at a few formulae real quick. resultant force may change the velocity. Right, right. So now I'll be showing you the experimental procedures to calculate the stiffness or the spring constant. Right. So this is the apparatus that you would use to determine the spring constant of an object. You have something called a retort stand. This is the retort stand. Uh, it's just like a stand for hanging stuff. This is an optical pin, and this is your load. Now, when you'll notice that uh, XO is your essentially your initial height in the sense, and when you add the load to the optical pin, this entire thing is going to drop down. This is a spring, by the way. This is a spring. So when you add the load, it's basically going to drop down to this level approximately, and whatever reading you get on the ruler at this point is xi. So your extension is x equals to xo, your original height, I guess, minus xi, your new or final height. And obviously you know the weight of the load. So you, after taking multiple measurements, you can simply record your results in a T table. That's a T table, not T as in the ones you drink. A T table looks something like this, where you would have load here, extension here. You just record your values, and then once you have your values, you can record it in the graph, in the load extension graph that I showed previously. Again, be mindful of your units. So using this experiment, the extension value that you get will almost certainly be in centimeters, meaning that your x-axis, the value for your x-axis will also values for your x-axis will also be in centimeters, and thus when you calculate the spring constant, you're going to get a value that's newtons per centimeters, and that's something you need to know. Right, so now we are going to talk about momentum, which is still under force. It's one of the effects of force in a sense. So momentum is the product of mass and velocity. The symbol for momentum is a capital P. So P is equals to mv. And I would like you, and basically a change in P is just mv minus mu. And recall that force is mv minus mu over t. So force is equals to change in P over t, which is mv minus mu over t. And again, you have F equals ma. Now, one thing I didn't mention before is that impulse, which is another value, you'll see a lot of questions about impulse in paper 2. But impulse has, first off, it has an SI unit of Newton seconds, not newtons per seconds, Newton seconds. Impulse is equals to Ft, force times time, or change in momentum, right? That's impulse. And also for F is equals to mass times acceleration. So that's momentum done. Basically, what you need to know is that if I have a body, A, let's say this is 5 kilograms, and it's moving at a velocity of 5 meters per second. That means that the momentum of A as it's moving is 5 times 5, 25 kilograms meters per second. So the unit for momentum is kilograms meters per second. Another thing you should know is, I guess, the law of conservation of momentum, where essentially what I mean is that if I have A, again 5 kilograms moving at a velocity of 5 meters per second, and I have B, which is, let's say, a stationary object, this is 2 kilograms. Once A collides with B, both A and B are going to be moving. A and B, so this is 5 plus 2, will be moving at a speed of, let's say, V, let's call it V2. They'll be moving at a speed of V2. Now you can, that's just what happens during collisions, because momentum is conserved during collisions or explosions. So, because momentum is conserved, you can say that m1 v1 is equals to m2 v2. So 25 kilograms meters per second is equals to m2. Here is 5 plus 2 because A and B are moving together as one body. So 7 times v2 is 25 over 7, which is just some 3 point something value. You can just plug it into your calculator. So that's the law of conservation of momentum. You also need to know that, this is one of Einstein's laws. If an object is placed on, let's say, a table, and there are no external forces acting on that object is going to remain where it's kept till the end of time. It's going to remain at rest. Subsequently, if I were to apply a force on that object, and there are no external forces like friction or air resistance that would act on that object, then that body would be moving in the direction that I applied the force in for an infinite period of time. You also, this is kind of obvious, but if a resultant force acts on a body, it changes the velocity it can change the velocity and can also change the direction of the motion or even its speed. And I mean, that's kind of just logical thinking. Right, so now we are on the last part of force, or the last part of forces. Not really. So we are on the second last part of forces, in fact. It's called centripetal force. The centripetal force is really just the inward force that's needed to make an object move in a circle. Think about, let's say, a planet with a rocket ship that's orbiting it. The reason that it's able to go in this direction, in this circular direction, is due to an inward force, which is the centripetal force. Now, the centripetal force of a body can be increased if the mass increases, if the speed or velocity, if the speed of the object of this body increases. Notice how I said speed and not velocity. That will be important later. Also, the centripetal force will increase if the radius decreases, because you're traveling you're traveling a smaller distance. Now, changing velocity, which is kind of something I alluded to a few seconds earlier. Since velocity is speed in a particular direction, when we say changing velocity, you can either mean changing speed or changing direction. What does this mean? Let's consider this object. A changing velocity can be something like this, where the speed changes as it goes in the east direction. You can see that this speed is changing. So you could say that this is changing velocity, but there's no change in direction. Or you can also say that a change in velocity is a change in direction. And it could be something along the lines of this, where over here, since direction is changing, you can say the velocity is also changing. Now, the second diagram here, let's call this A, let's call this B. This second diagram B, represents centripetal force, whereas A doesn't. So changing velocity doesn't really makes it really difficult to imagine or rather to interpret what you mean, especially with regards to centripetal force. And also, if something has a changing velocity, it also has an acceleration in the same direction as the force. So, with a circular motion, the acceleration is towards the center of a circle. Let's go back to the rocket analogy. Over here, the acceleration is towards the planet, and it might be difficult to imagine something accelerating towards a point without getting closer to it. But the object is always moving inwards from the position it would have had if traveling in a straight line. And that's kind of the basics of what centripetal force is. And yeah, right. Now you also need to know about something called drag, solid friction, which is just a force between two surfaces that may impede motion and produce heating. So let's say we have a surface here and we have an object C. If C is moving in this direction, there's likely to be a force in the opposite direction, which is called solid friction, that kind of impedes the motion of C. And this leads to energy loss in the form of heat. So some energy is lost, which is why eventually object C is likely to come to a halt. Now, friction or drag can also act on an object as it moves through a liquid. So it's similar to air resistance then, except it's liquid resistance. And as I mentioned, it also air resistance is also a thing. So drag can also occur as an object is moving through a gas, which is just a type, which falls under air resistance, if that makes sense. Now we've come to the moment of a force. Now the moment of a force is just the turning effect of a force, which itself is the product of the force and the perpendicular distance of the force from a turning point or a fulcrum. What that means is that the moment is equals to the force times the perpendicular distance. So if I have something like this, a beam balanced on a pivot or a fulcrum, and a force acts on this side. This is the perpendicular distance. This force F times the perpendicular distance is the moment or the turning effect that occurs on side A of the solid beam. Now, one thing that you need to consider here is that the point at which the resultant weight of the body acts is called the center of gravity. That means when I say that this beam is 2 kilograms, I'm saying that basically there's a point in this beam, usually just the middle, which is the center of gravity, and the resultant weight of the body acts at that specific point. And in the case of an experiment with a beam on a fulcrum, you need to ensure that the fulcrum is placed at the center of gravity for the beam, so that the center of gravity, which itself has a downward force acting on it, doesn't influence the moment of a force. Assuming you want to try and calculate the load, or you want to try and calculate the weight of an unknown load. Now, you also need to know about the principle of moment that states that for an object to be in equilibrium, the clockwise and anti-clockwise moments are equal. So basically F1 d1, which you can say is a clockwise moment, is equals to F2 d2, which is the anti-clockwise moment. And again, you can use this to calculate maybe the weight of an unknown load, or you can also use this in situations where one force on each side of the pivot, including on a balanced beam. And of course, you need to know the equation, and you also need to state that there's no resultant force and resultant moment when an object is in equilibrium. So at equilibrium, the resultant force is 0, and because anti-clockwise and clockwise moment are equal, there's no resultant moment. You should also be able to apply the principle of moments to other situations, including those with more than one force on each side of the pivot. What that means is that, let's say I have a situation where the beam is balanced on a fulcrum, where this is the center of gravity that has its own force, and now you have a load adding another force, and on this side I just have a single force. I would have to calculate two clockwise moments, one for C with its distance of, let's say, d1, and another with f1 with the distance of, let's say, d2 from the fulcrum. And when I add these two values together, I would get the anti-clockwise moment, and then I would calculate the clockwise moment normally, and those two would be equal. So you should be able to account for the center of gravity when calculating moment, and when calculating the moment of a force, and also apply the principle of moment simultaneously to that. And now you need to describe an experiment to demonstrate that there's no resultant moment on an object in equilibrium. So we can do that pretty simply. Let's do that right now. Actually, now that I think about it more, we have more or less just described an experiment where basically if the beam is balanced, that means that there's no resultant moment on the object, making it so that it's in equilibrium. So you just need to be able to explain that, which is kind of easy. Now you also need to be able to describe an experiment to show how to determine the position of the center of gravity of an irregularly shaped plane lamina. A plane lamina is just like a piece of card that's irregularly shaped. So I will try my best to explain it here, and I'll also, hopefully I remember this, but I'll link a really good video. It's a short video, it's only about a minute long, that also shows how to do it. Essentially, if I have, let's say, a plain card like this, I can hang it from a pin, maybe on a retard stand, and I can, it's going to swing once I do that. So once it stops swinging, I can apply a load over here, or a weight, and it's going to be in equilibrium, essentially. So I can draw a point line from here to here. I can then choose another point of the lamina, maybe something like this, and attach it using a pin here. It's going to swing back and forth, and eventually it's going to come to a rest, and I can apply the load again, and I just draw a similar line, and then the points where the lines intersect is the center of gravity. It's hard to explain over here, but like without really drawing it. So yeah, I will link the video in the description. Now you need to know, you need to have an idea of stability, where simple objects, when pushed a little and released, are likely to fall back to their original positions, and its position, and the position where it originally was a stable position. But if the regular object is pushed much further with maybe more force, it can topple over. And when it starts to topple as soon as its center of mass or center of gravity passes over the edge of its base. And from then on, the force of the box has a turning effect, which tips it even further. And a box with a wider base or a lower center of gravity tends to be more stable, at least relatively speaking. So it can be tilted with a greater angle or a greater degree before it starts to topple. And that's about it with regards to stability. And yeah, that's so we are done with forces from what I can tell. We are done with forces, and we can move on to energy, work, and power. which is a little long. Energy, work and power, then pressure, and we are finally done. Now energy. Energy is just the ability of a body to do work. And the unit for energy is joules, and it's a scalar quantity as I mentioned before. And energy has many different forms. Kinetic energy, which is EK, kinetic energy, and gravitational potential energy, which is GPE, the ones that are like most focused on in the IGCSE syllabus. But you also have thermal energy, which is something we'll be looking at when we do thermal physics, the next section. You have electrical energy, which we'll look at in section 4. You also have light energy and chemical energy and elastic energy. There are many different kinds. And you need to keep in mind that similar to the conservation of mass, you have the conservation of energy, which state and this is the law that states that it's a principle that states that energy cannot be created or destroyed. It can only convert from one form to another, or it can only be transferred between stores during events and processes. So you can convert electrical energy to thermal energy, but you can't create electrical energy out of nowhere. It's created from chemical energy usually, and you can't just destroy the thermal energy. Rather, it's likely to convert into some other form as you're using it. So that's the principle of conservation of energy, and you should be able to apply it to some examples as I just stated. So for example, a TV converts electrical energy to light, sound, and it produces some thermal energy. And you should be able to do things like this for some other examples as well. Now we'll be looking at electrical energy and gravitational potential energy more in detail. But before that, we should look at Sankey diagrams. So with the TV, right, most of this energy, it should be a lot bigger. Most of this energy is, right, as I was saying, if I have, let's say, electrical energy here, most of this electrical energy will be converted to maybe light energy, and then you'll have, I guess, sound will make up the second most thing. English, yeah, I think that works out. And there'll be very little heat, assuming that the television is efficient. Sound, yeah, that's how it works. So that's just a basic Sankey diagram. You'll notice that the larger the arrow, the more energy is converted into that particular form. So you should just know how to interpret them. And now we can go on to kinetic energy and GPE. So kinetic energy is the energy of a body due to its motion, right? I think we are all familiar with that. And there are different formulas that you can use for both of them. So kinetic energy, EK, is calculated using the formula half mv square, or mv square over 2, same thing. And again, energy has units, and this unit is joules. GPE can be calculated using the formula mgh, mass times acceleration of free fall times the height. You can actually calculate the change in GPE. Okay, you can also call it EP, just gravitational potential energy, EP. A change in EP is basically mg and a change in height, because the mass of an object is constant, acceleration of free fall is constant on planetary bodies, so on Earth it's a constant value. So the only thing that can change for a GPE to change is the actual height or position of a body. So that's what changing GPE means. And another thing that you should know is that EK, because energy is transferred, you can say that EK is just equals to EP. So mv square over 2 is equals to mgh. M and M can cancel each other out. V square is equals to 2gh. So velocity is equals to square root of 2gh. There was one question a long time ago that involved this formula, so I'm just providing it to you right now. You're welcome. Humble flex. Now we look at work done. So work done is just the product of force and the distance moved by the force. So work done is equals to force times distance, which is the same as energy. Which is the same as energy. Right, so work done is equals to the force times distance moved by the force, which is the same as energy. And basically it relates with how energy is transferred from mechanical or electric work done is equal to the energy that's being transferred, and that's just the concept of work done. And yeah, that's about it. Work done is change in energy, So mechanical or electrical work done is equal to the energy transferred in a machine, if that really So now you must consider energy sources. You have two main energy sources. You have renewable energy resources. Okay, let's look at the non-renewable ones first. Non-renewable energy resources. Now, they can be under non-renewable energy resources. You can obtain energy from fossil fuels and also from nuclear resources. And the main disadvantage of these guys are that number one, because they're non-renewable, the resources can be exhausted, and they also affect the environment in a negative way. However, they are very energy dense, and so they provide a lot of energy, and yeah, that's about it. Whereas with renewable energy resources, you have options such as geothermal, wind, solar, hydroelectric. You can use the EM waves from the sun, you can use the light from the sun, etc. These are all renewable forms. The main advantage for these guys are that number one, they aren't exhausted easily, and they don't pollute the environment, but they are less energy dense, and they don't provide a consistent supply of energy. They provide a variable supply of energy. And an advantage of non-renewable energy resources is that they provide a constant supply of energy. So that's pretty self-explanatory. You should also you should know that radiation from the sun is the main source of energy for all energy resources, except for geothermal, nuclear, and tidal. So tidal is brought about by the interaction between the Earth and the Moon. Nuclear is brought about by radioactive elements, by the splitting of radioactive elements, and geothermal is derived from heat and pressure that has been built up for some rocks, causing them to melt, and produce heat energy. Right, now energy is released by nuclear fusion in the sun. That's just something you need to know. And people are trying to carry out research on how energy released by nuclear fusion can be used to produce electrical energy on a large scale. This is just some emerging sciences in recent years. You should definitely know about efficiency. So efficiency is the measure of a material or the measure of a machine, uh, measure of the usefulness of a machine, that can be expressed as a percentage. So you have two kinds of definitions for efficiency, two formulas for efficiency. You can either do energy output over energy input uh, times 100%, or you can just do power output over power input times 100%. So again, energy is in joules, and in both cases it's output over input times 100%. But you might be asking, what's power? We'll be looking at this right now. Power. So power is just the rate at which work is done, or the rate at which energy is transferred. So power can be equals to work done over time, or power can be equals to change in energy over time. So the energy being transferred per unit time. And so yeah, that's about it for power. And now finally we can come to the last part under general physics, which is pressure. Right. Now pressure is the force per unit area, and pressure has a very simple formula: force over area, where force is measured in newtons and area is measured in meters square. So the SI unit for pressure is Newton per meter square, or pascals. So 1 Newton per meter square is 1 pascals, PA. And that's just something you should know. You can also express it as Newton per centimeter square, but Newton per centimeter square is not the same as 1 pascals. So that's just something you should know. Pressure has some factors. So for solids, the force is directly proportional to pressure. So the greater the weight of an object, or the greater the force applied on an object, the greater the pressure. And area is inversely proportional to pressure. So the lower the area, for example wearing high heels, the greater the pressure. And if you were to wear maybe flat shoes, then you would have then the pressure would be a lot less. But this is only for solids. There are different factors that apply to pressure in liquids, and you can really remember it using a formula. So pressure is equal to rho gh, where rho is the density of the liquid, g is the acceleration of free fall, and h is the height or the depth. So acceleration of free fall is a constant value, so that doesn't really do anything here. The density of a liquid basically tells you that the denser a liquid is, the denser a liquid is, the greater the pressure. And also pressure is directly proportional with depth. It increases with height. So you can display that with a diagram where you have something like this. The hole at the bottom basically goes the farthest, and that's about it. Yes, with that, we are done with general physics. And with that, we are finally done with general physics. It took a lot less time than I thought it would. I thought it would take 3 hours. It took less than half of that. But we definitely had to speed run it. But I do hope you took something away from this, and at least you were able to figure out what to revise, and maybe some of your doubts were cleared out. And with that, thanks for watching, and maybe consider subscribing if you like the video, and I'll see you next time.